So I'm very glad to introduce our next keynote speaker, Dr. Monisha Ghosh. Monisha Ghosh is a professor of electrical engineering at the University of Notre Dame and a member of the Notre Dame Wireless Institute. She's also the policy outreach director for Spectrum X, the first NSF Center for Spectrum Innovation, and the co-chair of the FCC's Technological Advisory Council working group on advanced spectrum sharing. Her research interests are in the development of next generation wireless systems, cellular, Wi-Fi, and IoT, with an emphasis on spectrum sharing and coexistence and applications of machine learning to improve network performance. Prior to joining the University of Notre Dame in 2022, she was the Chief Technology Officer at the FCC, a program director at the National Science Foundation, a research professor at the University of Chicago, and spent 24 years in industrial research at Bell Labs, Bell Research, and Interdigital, working on a wide variety of wireless systems of HDTV, Wi-Fi, Ethernet extensions, and so on. She obtained her Bachelor of Technology from IIT, right? In 1986, and a PhD from University of Southern California in 1991. She is a fellow of the IEEE.
Thank you so much. I know we're running quite a bit late, so I will try to do this as quickly as possible. It's always hard, following such an excellent set of talks that we've heard for money, to try and tell you something new, but I will try. I do want to say that the views I'm expressing today are just my own. They do not reflect Notre Dame or the Wireless Institute of Spectrum X. And I do want to acknowledge my excellent set of students who've done a lot of the work that I did. So I'm going to touch on a few things. We'll bring up the 6G. I know it's been mentioned a few times. I do want to emphasize again a point that was raised by Steven, where we have to think about racial divide being not only about people, but also about things. So the BEAD is doing an excellent job of connecting people, but it turns out that once you've done that, you have to think about the next step. Because if you really want to enable precision agriculture, smart manufacturing, remote monitoring of pipelines, all of that requires connectivity. And then I'll talk about my favorite topic, which is spectrum policies. How can you be intelligent about how you use the limited amount of spectrum you have? Share not only spectrum, but also share infrastructure. And then I will
+16282944.
So I just wanted to take a step back, actually. I started looking at this last year when I was looking at digital divide. And I wanted to look at, okay, how did rural electrification happen? Because in many ways, it's similar, right? It's a brand new technology, and it takes time, right? We are seeing the same progression in broadband as happened in rural almost 100 years ago. So by 1920s, you had widespread electrification in urban areas. And it took government stepping in 1936, so 16 years after that, with the Rural Electrification Act, to actually change this lag between what is happening in urban areas and what is happening in rural areas. And I'm sure the slides will be shared This is a really interesting paper that takes you about all of the things that happened. One of the key things that happened was working with co-ops. So again, trying to work with local communities who really are interested, who have a stake in getting electrification into their communities. And it, so it took 33 years from 1920s to 1953 to have 90% of farms having electricity. And today, nobody questions, nobody even asks whether, you should, somebody in a rural county should sell for less amperes or less volts than somebody in the urban areas. We take it for granted that we are going to do this. And as we think about broadband, we have to think about it the same way. It's going to take time, it is going to take money, but if we really think as a nation and as a international society that this is where we are headed, it has to be priority. Now, the next big question, is 6G going to solve the digital divide? And I know, Mrs. Slim, no apologies to what you mentioned. I think there is a lot. And if you really think, if you drill down and look at what 6G is actually proposing to do, I don't see any way that it's going to succeed if 4G and 5G have not, honestly speaking, especially when you're talking about rural connectivity. New bands for 6G are mostly going to be higher, even if they're not millimeter wave, even if they're the FRP bands, they're going to be higher. It's not going to address indoor connectivity. Sitting in here and I've been taking measurements, I can barely get 4G. There is no 5G inside this building. There is Wi-Fi, but there's no 5G. Spend most of our time indoors. And so as we think about what connectivity means, we have to think about how people spend their times and where they need the connectivity. Well, 5G has yet to meet its metrics, even in urban areas. So if you look at this figure, which is actually quite old now at this point, this was the US the office. They did this comparison between 4G and 5G. And you might say, okay, we're only halfway through 5G, so we really can't say we met the metrics. Okay, let's look at 4G. And let's see these metrics. And if you really look at it carefully, except for maybe the user experience data rate, most of these metrics are not made. So I think as we, especially when we talk about connecting, getting connected, let's not jump to the conclusion that 6G is going to solve our problems, because I don't think it is. The other thing to keep in mind is doing this new generation every 10 years. I mean, it's an industry-driven thing, but does that really solve the problems that society needs? We need more bandwidth, technology evolves, but this constant 10-year cycle where you rip out infrastructure, maybe you add more new infrastructure, add bands, add devices, it works to some extent. So we really have to rethink how we live it. What I'll show you later in the next few slides is that really, as with electrification, the key is infrastructure. And if you don't get that infrastructure, no amount of spectrum is going to help you solve this problem. In fact, if you have even 4G and it's deployed well, you can address a lot of concerns. As I said, I'm just getting 4G here, but it's aggregating 3 carriers, and I get 80 to 100 megabits per second. Why do I need an 4G? Why do I need 6G, right? So trying to tailor your solutions to what you need is very important. 6G has a place for sure, but doesn't have a place in increasing connectivity for everyone. So this is some data that I came across recently. This is it's a 5G observatory scoreboard. It's pretty recent, it's June 2025. And what it does, it looks at comparison of 5G rollout and the comparison of spectrum. And it has EU, Australia, Brazil, China, India, Japan, South Korea, UK, and USA. I've picked two things to highlight here. So if you look at South Korea and the US, and you look at the number of 5G base stations per 100,000 inhabitants, South Korea is way out. It's 670 base stations per 100,000 compared to only 42 in the US. The next highest is China at 301. Now you compare with the amount of spectrum these guys have, and you'll see that South Korea actually has less mid-band spectrum than the US. I don't know, I mean, I'm sure most of you are not involved in spectrum policy as much as I am, but I'm tired of hearing this notion about how US is losing the race to 5G to China because we don't have spectrum. If we are losing the race, if there is a race and we're losing it, it's not because of not having enough spectrum, it's because we don't deploy. And I do realize there are a lot of hurdles to deployment, siting, location, getting permits, rolling it out, all of that. It's money, and that's absolutely true. But if you don't do that, just throwing more spectrum at the problem is not good. And that has consequences. So if you look at the deployment density and then you look at rural coverage, South Korea, with the greatest density of base stations and not the largest amount of spectrum, is almost 100% 5G rural coverage. So if you really want to get to the point where you're trying to get your population up connected, and you neglect this very, very important piece, you're just not going to be stuck. You're going to be just staggering the same. I want to switch gears a little bit and talk about precision agriculture. It has been brought up a few times. The SEC, like the Technological Advisory Council that both Henning and I are on, they also have a task force on precision agriculture, which looks at, and this was the most latest recommendations from December of last year. And they just did a really good, it's a very nice report, and the link is there, which talks about what you need to really get precision agriculture. And a few things that they pointed out, one of them was improve your mobile maps, improve your wireless maps. Because even today, even with what you heard from NT Factors others, everything mobile is geared towards a phone. There are no people using phones in the middle of fields. There are tractors, and they need connectivity if you really want to do precision and agriculture, right? So how do we get beyond just mapping spectrum and mapping broadband to where people are and how people are using the network to how this future generation of devices of things? And when I think about IoT, I think about little things, but a tractor is part of an IoT ecosystem. And then, of course, some of the things I've already mentioned is you have to build out a robust broadband infrastructure to help ensure last mile coverage. We talked about last mile coverage, which relates more to people. But when you talk about precision agriculture, I've talked to working farmers who talk about how their tractors get stuck on the side of a hill because as soon as they're on the other side of a hill, they lose connectivity to their LTE, there are no 5G, it's LTE base station. And then somebody has to go out there and sort of manually move it over, right? So you really need connectivity over every acre. Now, is it feasible to do this over a public mobile network, like have the tree carriers do it? I think not. And that's why we have to be more smart about how we use it. Agricultural sector, at the end of it, is a huge sector in many economies in the world, not just the US. And if you really want that sector to grow technologically, connectivity becomes very, very important. And the last bullet was, kind of addressed in different contexts, but it applies to precision agriculture as well, is especially for people engaged in this industry, having education and training. The recommendation was actually to do partnerships with land grant institutions who are set up to actually work with agricultural communities. This was a recommendation from the task force. None of these recommendations are binding on the FCC or any government, but I think they're really well thought out directions. So let's move to shared spectrum. I know, Professor Sarfur, you mentioned that I talk about TV white spaces. I'm sorry, I'm not going to be talking about TV white spaces, but I will be talking about shared spectrum, and I'll talk about CBRS and 6 gigahertz. I did work on TV white spaces for a very long time, and I still remain disappointed that it never really, got the, I worked on it to create the 22 by the way as well. So it's sad that it never really took off. But I think if you look at CBRS, you'll hear two sides of the story. But then, the numbers really tell you what the story is. And if you look at the numbers, CBRS, remember, even though and for those who are not from the US or don't know the details, CBR is a shared spectrum. It is spectrum that the primary user is Navy radar, so it is used by the military. But because Navy radars are sporadic, they're along the coasts, it was actually, the whole thing started in 2012, the study of how the spectrum could be shared. But the spectrum didn't really get auctioned until 2020. So it's really 5 years old. And when people start comparing the rise in CBRS versus the public cellular network, they forget to keep in mind the time scale over which these two networks have evolved. So in 5 years, really, when the auction happened in 2020, the growth has increased tremendously. Today, we have 420,000 deployed CBSDs on the last line. And if you look at the growth in rural areas, it is actually growing very, very fast. So 67.5% of CBSDs, and this is data from last year, were in rural census blocks. So clearly, some of the applications I mentioned, precision agriculture, it doesn't make sense for an AT&T or T-Mobile to deploy a network that is covering every day. But suppose you can now, John Deere has CBRS licenses. If they deploy localized network where the tractors are, and you take advantage of that spectrum where you need it, and it moves with you with a sufficient backhaul, you can actually get this coverage from it. So a lot of other numbers. The other number I want to point out is that CBSDs, which are CBRS stations or CBRS access points, can be two kinds. One is general authorized access, where you don't have to pay for a license. It's almost like unlicensed, but the technical term is licensed by rule. So you have to access a database, get authorization to use a band, and then you can use it. And PAL, which is a priority access license that people actually pay money for. And John Deere have actually bought licenses. Verizon has bought licenses. Many people have bought licenses. But if you look at the growth in the license by rule or the GAA category, that is huge. So Verizon will use their PAL licenses, but they will also use GAA licenses because it's free to use. And I think in one way, if you think about how CBRS has evolved, it is, in my mind, we should be following that model. So spectrum is not allocated to somebody and locked away until they decide to deploy. It is a common pool. So even a PAL licensee, if they have not deployed in a certain area, others can use that band under a GAA license. As soon as they deploy, they get primary access to it. But having this very flexible way of using spectrum, keep in mind, CBRS is only 150 megahertz, which is much, much less than a lot of the 5G spectrum that carriers have. And there are a number of examples of how CBRS is being used. But let's move to, real deployments. What I told you was the numbers across what's happening in the country. But this is a real deployment in actually South Bend, where Notre Dame is, where during the pandemic, the school district realized that there were a lot of low-income households that did not have broadband internet at home. So they set out trying to figure out how they could address this problem. So they took advantage of dark fiber. So, the good thing about fiber is you lay it, you may not use it right away, but it is there. So there is a local nonprofit that owns a lot of the dark fiber in the city, Choice Light. They lit up some of the fiber going to the schools and to towers. They used two schools, the primary, the two schools over here that they installed these base stations on, and two towers that they installed it. So it's a very, very dense deployment. This is not like an experimental deployment trying to sell, a set of households. And what has happened is that now 5,000 low-income students and their families have access to free broadband using spec. And the reason you could do this is because you have spectrum. The equipment is all 4G. So again, it is not so much the technology that's important here, but having the spectrum to deploy the technology in. A lot of these CBRSs are now moving over to 5G, and you get some improvement doing that. we started studying this deployment in very detail because we had other goals in mind to study propagation and interference and all of that. And then we started studying this about 2 years ago. This was the only use of CBRS in that area. Over the last year, Verizon has started deploying their C-band network, and they're deploying CBRS across the entire band, right? And so that does bring some challenges in with co-channel coexistence and adjacent channel, but nevertheless, they're perfectly legitimate users of the band as well. But whatever service they offer is obviously only for a Verizon customer, and it's not free. This is not a unique example. There are many, many school districts in urban areas. So when we think about connectivity, it is not just providing connectivity options because you don't have any, but doing it as an affordable or free basis, right? South Bend, we have all the three carriers, we have fiber, we have cable, we have all the other broadband modalities that you can think of, but and there's always going to be a certain section of the population that will forego that broadband connection to go to the another really nice application of CBRS that I'm actually personally very excited about, and I hope this can grow, is you can use this shared spectrum to also deploy shared infrastructure. One particular example is that of a neutral host. And we've studied some of these deployments. We actually are in the process of setting up one in our university for deeper study, is if you set up a CBRS network, say in this building, right? And you have agreements with the mobile operators so that when you're a T-Mobile customer and you walk into the building, you hand off to the network inside the building. So it's seamless. From a user perspective, it's still T-Mobile showing up on your phone. But from everything else, you have created a lot more efficiencies. So for example, you're not trying to connect to a macro tower sitting outside and going to 20 dB of building attenuation both ways. You're not transmitting as much power. I don't have the details, but I'm happy to share the paper we wrote. The power consumption on your mobile goes down tremendously because now you're just transmitting enough power to reach a CBSD in the building, rather than, again, go through 20 dB of propagation loss. The other thing that people don't realize is when you do that, this is you're actually creating more capacity for the outdoor network by releasing a bunch of resource blocks. So when you move inside and your signal strength drops, you're actually occupying more resources in the network. By not doing that, you've created capacity for the outdoor network on the licensed spectrum that they already own. So having a little bit of spectrum, it's only 150 megahertz, as I said, that can be shared, and you can have shared infrastructure that operates over the network, gives you a lot of options. Now, you can use it as a neutral host. You can also use it just as a private 5G network or a 4G network, which many people are doing in hospitals and factories. So most of the automation that's happening in Amazon warehouses, for example, where you have robots roaming around picking up your packages and making them ready for delivery, most of that is happening for CBRS. Because that is the only kind of spectrum that gives you the quality of service. Wi-Fi cannot give you that same quality of service that you need from a cellular system, that cellular system can. The other band, which I'm very excited about, is 6 gigahertz. Again, 6 gigahertz, for those of you who are not aware, in the US, it's 1.2 gigahertz of spectrum that has been made unlicensed, but it is also shared. So you have existing incumbents, and most of these incumbents are these fixed links, long power links. They're still there. They haven't gone anywhere. They haven't been relocated out of the band. But because of the FCC rules that have been created for low power usage, and there are actually 3 tiers of use. One is indoor, low power, indoors. So this is, you can buy Wi-Fi 6E is the lane that goes by. You can buy an access point for indoor use only. It doesn't have to do any fancy dynamic spectrum sharing. The only knob we are turning here is power. They're not allowed to transmit more than 5 dBm per megahertz. It turns out that's enough for Wi-Fi. You can have things like outdoor Wi-Fi access point, which can transmit higher power, standard power, which is up to 36 dBm. But in order to do that, you have to go to a AFC or an automated frequency coordination system. 5G, I mean, unlicensed is not just Wi-Fi. You can also do 5G NR or NRU if you want. Nothing stops you from doing that. The latest ones that are coming out are the smart glasses, which are using Wi-Fi to communicate with your phone. And so by making a large section of this band unlicensed with very loose rules, you can enable way more applications and use cases than if you were to clear out part of it and auction it off, which some countries are doing, right? But I personally feel that this band at 6 gigahertz, if you try to do cellular base stations, normal cellular in here, you have to go through about 20 to 30 dB penetration loss to get inside. So you're going to end up with a cellular network that is small cell that's outdoor only, very much like the millimeter wave. Finally, I want to talk a little bit about mapping. We had a really nice presentation earlier today talking about mapping, and I just want to emphasize what Henning also mentioned, that we have to go beyond just throughput. We have to look at, even if you're looking at throughput, you need to look at both downlink and uplink. You have to look at latency. We have to look at signal strength. When you see 5G on your phone, I can guarantee you that most of that data, unless you're on a T-Mobile standalone network in the US, is not going over 5G. It's going over 4G. So unless we can separate out these nuances of how spectrum is being used, we'll constantly be chasing these Gs and thinking it's going to solve all our problems. So within Spectrum X, which is the NSF center that Notre Dame is the lead PI, we've created some apps, and if anybody wants to test it out, I have a phone with that app running, where we are collecting, we are doing, you have to come up with a good term for it. It's not really crowdsourcing, it's kind of intentional sourcing, where we are trying to improve the quality of the data we collect so that we don't give it to everyone. We have projects where students go walk around with phones and collect this data, and then we analyze it. And we've been able to draw a lot of conclusions. Finally, this is another example of a project we did where this was more on the broadband side, not wireless as much. We conducted a study with the city of South Bend over several months. We took 40 households in South Bend and we installed simple Raspberry Pi monitoring devices. When I say monitoring, all it was doing was running speed tests and collecting data on Wi-Fi and other aspects. And one of the results from that, and we have very many, which I think addresses what Henning was trying to say, is that yes, you can do fixed wireless access, but these are two links. This is fiber, this is fixed wireless. Fixed wireless performance and over a cellular network, so it varies. It follows the cellular curve. In the middle of the night, you get great performance when nobody is on the cellular network. And then during the busy hours, it drops, both downlink, uplink. And the latencies are really, really high. Really, they're like 600 milliseconds. Compared with a fiber network, which has 600 megabits per second, but it's flat 600. And this is accumulated over an hour. Uplink, downlink, rock steady at 600 megabits per second. Latency looks like it's similar, but actually the scales are very different. We couldn't put it on one curve because this latency is over 20 milliseconds, this latency is over 800 milliseconds. So a huge difference. We're also doing a lot of study on Wi-Fi because much as I like unlicensed spectrum and shared spectrum, I don't think Wi-Fi folks are utilizing all the bands they have efficiently. So if you look even at the 5 gigahertz and you look at all the bands that are available, everybody goes to Uni 1 and Uni 3 because they don't have DFS requirements. But our DFS requirements are really not a big deal. Every access point pretty much in the market actually implements. So it's really an ecosystem that has developed, which has shied away from certain bands for so long that they're not using it. And then you clamor for more spectrum. So I think the bottom line is the independent, unbiased measurements of every piece of spectrum that's out there is absolutely essential for us to know what to do next. And this is my last slide, some closing thoughts, which just summarizes what I've been talking about. We have to connect everyone. One of the things, the second bullet I should really point out, I often hear, oh, 25 megabits per second is enough for rural. Thinking no, because everything that we have on the internet today is designed for a much higher experience, right? Just as with electricity, we don't differentiate with how much voltage you get in rural areas versus urban areas. We shouldn't be putting these artificial barriers as to what is acceptable in certain communities versus others. And I really think we can do better spectrum policy to make a lot of these technologies that we have better able to serve actual fields. Stop here, happy to take.
Hello? Yeah, just speak loudly to the phone.
This one. Thank you for this. Am I audible? Am I audible?
Yeah, just go ahead.
So, question here is.
So that's
They're working here. Audible? Yeah, thank you. Thank you for this presentation. So, the biggest problem that we have seen with CBRS is interference. That's the biggest challenge because it's free for all. Anybody can use. But hunting that interference, solving that becomes a big challenge. So it's good for industries which have big areas, like John Deere is an example, or if it's any other, like say Disney, if they're using it, then it makes sense for them to avoid that. So that's one thing on the on CBRS. But coming back to the spectrum, since you are more focused on spectrum is a real estate which is not going to shrink or increase. So it needs to be used well. But what I see is that, I mean, the technologies that they have defined with each G, 3G, 4G, 5G, they have come up with technologies. And recently, what is being used is OFDM technology. So nothing has come after OFDM. Same way, nothing has come after, say, QAM or multi-user MIMO. So we are kind of like stuck there, which essentially means that even though you have the spectrum, you try to piece it, puzzle it, and give it to everybody, you will not be able to use it to the max after a certain point. So how do you see this? What is next after OFDM or any other technology which can solve this problem?
So let me address your first question. The CBR is interference. So we've done a lot of work on that. So that deployment I showed, actually we kind of dug into both the co-channel and the adjacent channel interference concerns. And what we realized is the SAS could actually be doing a much better job managing this. And if you go back and read the original CBRS rules, there wasn't a mandate for the SAS to do it, but there was a recommendation that the SAS manage GAA coexistence, right? I think a lot of that is a technological problem that if you implemented better frequency management procedures, either natively as part of your 4G or 5G or over the top, you could do better. There's a lot of feedback, and we figured out problems just by data that we collected on our phones and fed that back, and then so those I feel are technological hurdles that actually can be solved by a combination of device-based adaptation and the SAS. The other part, actually, we wrote a paper last year where we again did a lot of measurements, and that was actually the question I was going after, that in the transition from 4G to 5G, are we getting high data rates just because the bandwidth went up, or did any of these technological advances actually make a difference? So you mentioned massive use, MU-MIMO. MU-MIMO has not been deployed in the US as far as we know. It's MIMO with panel antennas on radio stations. The QAM order is, I think, max 256. They haven't gone beyond that. MIMO, the maximum stream efficiency you get is 2, sometimes 3. You don't even get 4 because that's the reality of the channel you have. The only thing we found that made a difference was if you deployed densely, you had a lot more base stations, and we compared the 3 carriers, and I will name them because none of them funded my work. I was funded by myself. T-Mobile has the most densest deployment in the urban areas we mentioned. And what happens when you deploy densely is you have an average signal strength, which is much better. With Verizon and AT&T, the signal strength was up and down all over the place. It was much less uniform, and that resulted in much poorer MIMO performance. You could not sustain the high number of layers much. And the thing is there something better than OFDM and MIMO? No, right? And honestly, I feel the spectral efficiency, the bits per second per hertz theoretical that we have is pretty good. So I think we have to focus more on how we deploy rather than push the technology angle in 6G so much.
Thank you. Can I, you have a question?
Yeah, I wanted to ask a couple of
Turn it on,
questions.
just one question.
Very short. Earlier you mentioned that the 5G hasn't really addressed the problem of connecting the unconnected. And you can see how 6G is going to do that. Made that statement. But if you look at the 6G reference diagram from ITU, while 3G had these three quantifiable requirements of EMBB, RLCC, and the 6G has some of the societal considerations of ubiquitous connectivity, connecting the unconnected, and two others. So then, how are those goals going to be met? I'm trying to finish. But some of the talks I'm hearing, people are saying that 6G is about bringing the cost down, making it more affordable. That is going to be the design principle right from the beginning. Whether that happens or not, I don't know. So maybe you want to comment on that. The second very quick question is, what do you think about this notion of network slicing? Because we have this basic, internet, as we know, is the best effort, one quality of service, but people have been working on network slicing. And when I think of a slice, that is just for the rural connectivity that is costed low. So do you have any comment on that? Is that ever going to happen or
So
not?
let me address your first question before, right? If, as the previous gentleman said, 6G is still OFDM, it's still MIMO, the low-cost 6G is just 4G. In my mind, low-cost 6G is 4G. That's it. If that's what you're going after, I don't see why you want to go to the extent of deploying more infrastructure, upgrading your phones, and doing all of that, right? So you can do 4G has actually been the breakthrough over the last Gs. Honestly, if I look at the Gs, 4G clearly, they've got a lot of things right. Channel aggregation. I can aggregate up to 5 4G channels on my phone, and on 4G, and we've got these numbers, you can get close to 800 megabits per second if you're doing it right. So I don't understand what 6G is trying to do with this low-cost thing. If you're not going to change the physical layer, low-cost 6G, go back to 4G. Second part, which was network slicing. I am not a huge, I don't think network slicing is really going to solve any problems that are real. The biggest issue is, and this is something we don't talk about as much, one of the fundamental constraints in the way we've designed 5G to be TDD is you're always stuck with this uplink downlink split, which you cannot change. So if there is a network slice, for example, security monitoring cameras or something else that requires a lot of uplink traffic, slice is not going to help you. It is still slicing along the same TDD split. Slicing, I've looked at people who have tried to look at slicing for, say, factory automation. It's not reliable. They'd much rather have a private network inside the factory that they control rather than get a slice that the operator gives to them, which, is still a slice. It's not the full, they don't have control of it. I'm sure slicing will help some applications. I don't think it's a solution for unconnected content.
Thank you. That's interesting. You're slicing, what part of the slicing ran or end to end, right? All right, let's thank Monisha. Do you want to come down? Right, so there is a slight change in plan. There are 2 people who have to take a flight, one from BWI, one from Reagan. So we have to give priority to the person who is going to BWI. Both of them. Right.